Okay, welcome. I want to start today's lecture with fixing the stuff from the previous week. And yeah, so we had a proof that was slightly flawed. I did a few small hand wavy last week, and there was actually a hole in that proof, so we're going to fix it and doing it properly. The line of the proof will be more or less the same. It will be this congested minors, congested shallow minors things. And the proof will be more or less the same, but we need to be slightly more careful with counting overlaps of them. Okay? So what we wanted to do, we wanted to look at, when we look at what was the depth congested minors, yeah, the depth A, C congested minor. Yeah, it was H is a depth, of G. If there's bigger branch sets, if for every V, say H in H, there is there's a set VH that's connected. Yeah, that was connected. For every edge, H1, H2 in E of H, these sets touch, which means that they overlap, or there's a match between them. Okay, and second thing, so in the normal minors, we had that they're disjoint. Here you can use every vertex node C. Yeah, so for every V in P of G, the number of H in H of H such that V is in PH is at most C. Okay, so we can use every vertex from G at most C times. This corresponds to taking every vertex of G, blowing up into clique of size C, and then taking a normal depth A minor. And here depth A means that end of radius. Okay? Yeah, so now this is the same as blowing up every vertex in a clique, but we prefer to have this definition. And we had a lemma saying that depth, like bounded congested minors are still sparse. Yeah, so we had a lemma saying that if G was, I think it was G hat or something like that, is a depth A congestion C minor G, and there is some integer B, then the nablas B of G tilde are bounded by something, and there was like some constant, it was C minus 1/2 as far as I remember, plus something times nabla, and here was the natural thing A plus B of G. Okay? So what we had was that if the graph G is somewhat sparse, has got small nablas, then depth A congested C minors are also sparse. I mean, they have sparse shallow minors. And we have made some proof, and there was some hand wavy part which was not really completely true, so I want to fix it now. So what I want really to prove, I mean, we have an observation that we started the previous proof, and this is the true observation, was that if I take I mean, there was a lemma some time ago that if I take depth A minor and depth B minor of this depth A minor, then it's really 2AB plus A plus B minor of the original graph, yeah, because every connection of length roughly to B inside there. Okay, so this is like minors. So with congestion, it is the same. I mean, if you use on the first level of pi, you use every vertex at most C 1 times, and on the second level, you use at most C 2 times. Then in total, you use every vertex at most C 1 times C 2 times. You can verify it, but if G2 is if G1 is depth A congestion C minor of G1 minor of G0, and G2 is depth B congestion D minor of G1, then actually G2 is depth as before 2AB plus A plus B, and congestion multiplies. This is C times D minor of G0. Yeah, so I mean, if you, this is the standard proof, the same proof that we had for like without the congestion. So this is the observation. So what we really want to prove, that congested minors are sparse and they have got just few edges, because this is really like, this is like congestion 1 depth B minor of congestion C depth A minor of G. So it's really like a this depth congestion C minor of G. So what we really want to prove here, what we really want is that if H is a depth A congestion C minor of G, then the density, like the number of edges of H over the number of vertices of H, is smaller than, and here I will use my notes to write the formula without errors, C plus 2C squared A plus 1 squared times nabla A of G. Okay? That should be enough of the notes. Yeah, so what I really want to say is that if I have a depth A congestion C minor, then really the density of this minor is bounded in terms of like depth A normal minors, but there is something in front, and this in front is some polynomial really of C and A, and there is some C in front. This was the additive front from like, this was the density of these cliques. It was here better, previously was better known as C minus 1/2. We'll put C here just with a slightly different notion of degenerate edges, but this more or less comes from these cliques that we insert. This is like the density of these cliques we insert at every vertex, and this is like the blow up of density we can get from using the congestion, but it's not very much on top of the normal minors. Okay, so that's like what we want to prove, and we'll try to use, I will now show you the proof, which goes along the same lines as previously, but I mean, slightly different. Okay, so yep. So let's fix this branch set. So let's fix this model CH for H in V of H. Yeah. So this is this model of congestion C at depth A, and inside every vertex we choose the root. Yeah, as before we choose like for every H, we choose for V of H. So V of H. This is like the guy such that everything else is within radius A. Yeah. So that's VH. Every, like, this is like the center. I will write it just the center of V of VH. Yeah, the guy that, so that everybody H in this branch set is within radius A from V of H. Okay, so this is the center. And now I want to count the edges. So I want to count the edges that stems from really like sets really overlapping each other. And I want to count edges stemming from really like sets that overlap a bit, but there's really some connection going on there. Let me say it through. So like I want to say that an H, H1, H2 in E of H is degenerate. And previously we thought that really these centers are the same. And now I want to make it slightly more general. I want to say that if like on top of one of the centers another branch that exists. Yeah, if H1, if V of H1 lies in the branch set of H2, or V of H2 lies in the branch set of H1. Okay? So it's really like whenever one branch set swallows the center of the other branch sets, then we say that this H is degenerate, and intuitively the degenerate edges will be counted here, the density of degenerate edges will be counted here, it will be bounded by C, and that will be quite easy, and the slightly more complicated thing will be like the non-degenerate edges can be somehow like flattened to get a normal non-congested minor, and in this case we'll get this bound here. Okay? So let us bound degenerate edges. What I want to say is that, well, if this happens, I mean, I want to charge, I mean, how many times this can happen? I mean, for how many the edges H1H in E of H, we have got that VH1 is in the branch set of H2 of H. For how many edges we can have this option? Well, at this place, this is one vertex of G, and at this place there are at most C guys from the at most C branches, including the guy from H1. Okay, so this is, I mean, at most, the congestion implies that there are at most C minus 1 such edge. Okay, so every degenerate edge we count once from the. I mean, if in a sense, if you look at this degenerate edge, if this happens, we charge it to H1. If this happens, we charge it to H2. Yeah, so we charge if H1, H2 is degenerate, we charge it to H1 if V of H1 lies in VH2, and charge it to H2 if V of H2 is in VH1. I mean, we choose otherwise, yeah, so if this happens. Okay? And now what happens is that every vertex gets charged at most C minus 1 times. Right? Every edge is charged to something, and every vertex of H is charged at most C minus 1 times, which means that the number of degenerate edges is at most C minus 1 times the number of vertices of H. Yeah? Every vertex is charged at most number of times, and every vertex is charged at most number of times. Okay? Which means that this corresponds to this C here. I could have put here, let me take colorful chalk. This means that in this proof I could have put here C minus 1, but it really doesn't matter. We put C here for making this formula relatively simple. The main point is that there is like, this is linear here, and there's a squared, there's a polynomial of the radius in front of it. And what really happens to the constant C is not really matter. You can think of C being a small constant in most of the uses, and the dependency on radius is the more important part. It's like multiplicative polynomial factor here times linear factor of the density. That's the more important part of this formula. Whether it's C or C minus 1 really matters very for our later applications. Okay, we have handled degenerate edges. I'm going back to this board to handle non-degenerate edges, which are more interesting. Now, in a sense, we want to flatten. I want to wipe out this one as well. We want to flatten the model, and we will flatten it in a random fashion. What do we do? We pick a random order of the vertexes. So let's pick a random order. Random order of V of H. So we order randomly. And now, at every vertex V of G, at every vertex, the boss, I mean, we look which, so at every vertex there are at most C branches overlapping there, okay? And we say that the boss here is the largest guy up there. So I want to say that the boss of V, which is in V of H, is the maximum, maximum H such that V is in branches of H. Yeah? So in this vertex V there are a few branch sets overlapping, and I choose as the boss the largest in this order, like the most. You can think of this as priorities, as drawing random priorities, and the top priority up here is the boss up there. The boss is undefined if this guy is not using any branches. We will use only bosses for the guys that are in some branches. Okay? So this is the boss, and intuitively what I want to do, I want to, okay, and let me write it down, and let's write a non-degenerate edge. So let's look at H1, H2 being a non-degenerate edge of H. So how does it really look in the graph? Well, here is V of H1. Here is somewhere the graph V of H2. Okay, and there is somewhere here. Let me use two colors. Up there. This one. Okay. This is somewhere the blob BH1. This is somewhere the blob BH2. Sorry, BH1 and BH2. Sorry. BH2. Okay. They can overlap. There be just a net between them. But because this is a non-degenerate, this blue doesn't contain VH1, and this one doesn't contain VH2. I mean, this one doesn't contain VH2, this one doesn't contain VH1 because it's non-degenerate. And now I want to say that I want to draw here a path, so I can take a color and go like a path, go up there, and then jump here and go here. So this is some path path pH1, H2 corresponding to this edge, and I want to say that this path is good if whenever I'm on this path, first this is yellow, orange, H1 is the boss here, and H1 is the boss here, H2 is the boss here, and either H1 or H2 is the boss when they overlap. So I just like really, okay, maybe I draw it like this, because I thought it like this is the overlap. Okay, I thought of this as an overlap, but didn't draw it well. Okay, it goes like this. So I want to have here being the blue, the H1 being the boss, here being H2 the boss, and here being one of them as the boss. I mean, one of them will be drawn as the better one, as the higher priority one, and I want here to be one of them being the boss, here H2, and here H1 being the boss. Okay? So H2 is good, if along PH1, H2, H1 or H2 is always the boss. Okay? Okay? And I want to say the following. Let's look at the following. We need now two observations. The first observation is as follows. I want to take VH2 and contract onto VH2 everything that I can contract where H2 is the boss. Like, take the following minor. Take minor of G. For every H in V of H, such that H is the boss in the root, so this really here is the boss, I want to contract onto H the whole connect, I will write all possible V in V of G, where boss of V is H. Okay? So what I want to do here is that I want to take a vertex V, okay, V onto V of H. Okay? There's V of H here, there is the blob of this V of H somewhere here, okay? And maybe in this area H is the boss, and maybe there are some other areas where H is the boss. Okay, this can be disconnected. There can be like another blob coming in with higher priority that disconnects the places where H is the boss, and I want to take this part and contract it onto V of H. Okay, so I want to contract whatever I can. This one I can't contract without violating this para. So I want to take this connected component of this BH that where H is the boss and contract it onto H. Okay, and the first thing here is that this is a depth A minor, because I'm contracting like a subset of the. It's not that obvious that I will go along the shortest paths, but there's actually I cannot do it as it's obvious as here, because I want just to contract this path. So I want to contract this one, but only radius A. Contract keeping it. So I write keeping. I try to simplify things and I fail at depth A minor. So I want to contract things, but I want to stop at depth A. So I don't want to contract more larger than A. So I really want to like contract things of radius A here onto the sphere of H. Okay. So the observation is that because I do it cut at distance A, this is like depth A minor. But the important thing I want to say is that I will contract this part. I mean, what I want to say here is that for every this minor will keep, this minor keeps good edges. In a sense, let's look at this picture. What I want to say is that, okay, let's say that blue has got higher priority than orange. Okay, that H1 has got, let's say that H1 has got higher priority than H2. And I want to say that everywhere here, H1 is the boss. So this one gets contracted here. Everywhere here, H2 is the boss. So this one got contracted onto H2, which means that this edge will be a real edge in this minor. We can keep this edge in the minor. Yeah, there will be like this will be contracted onto H2, this will be contracted onto H1, and this edge here, we can keep it in the minor, which means that all good edges will survive. Okay. And this is the normal non-congested minor, yeah? We just contracted the guys. I mean, we use every vertex at most once. We contracted only on the boss. I mean, vertex gets contracted onto the root of the boss at this place. Okay? Which means that, and all good edges are kept, but how many good edges are kept? I mean, the point is that, let me put it here, what's the probability that an edge will be kept? What's the probability that a non-degenerate edge, H1, H2, is good? Yeah, so we take a good edge, and what's the probability that it will be good? Well, the point is that, well, we have got a random order, and there is like a path, okay? And how many other blobs, let me take yet another color, hopefully, there is something like here, okay? Well, there are some other blobs coming here, and you want all of these blobs to be of lower priority than the orange one and the blue one. Okay, we want them to be of lower priority. But how many these guys will meet? Well, this path here, H1, H2, well, it's of length. Well, it has got this blob of A and this blob. So it sees A plus 1 to A plus 1. I think it sees 2A plus 1, sees 2A plus 1 to A plus 2 vertices, yeah, because this is like length A here, and length A here, and then an edge. So it sees this number of vertices, and at every step, it sees C minus 1 other blobs apart from these two. Okay? So this is times C minus 1, and plus these two extra blobs up here. Okay? So this is the number of blobs this guy sees, the number of other blobs. And out of these blobs, we need, these guys to be the top two. So we take a random order, we see this many blobs, and our two favorite ones, the blue one and the orange one, needs to be the top priority ones. Okay? So I have got at most this number of blobs. This is like, this is less than, I want to say that this is less than the number here, 2CA plus 1. Okay? I want to say, I hope this is true. Yeah, it's true. Okay? So this is this number of blobs, and at most, out of these blobs, I want the two guys to be the top guys, to be the two top guys in any order. So this probability, I think I wanted to, I was hoping to have here there, but I want now to say that this probability, I would put it here, sorry. I want to keep it up there without wiping out this one. So this probability that H1, H2, which is non-deck, is good, is at least 1 over this number, choose 2. Yeah, this is like, I have got these guys, and my favorite two need to be the two guys, but any permutation of these guys is equally probable, which means that I just the number of choice of two guys as being the top two guys out of all of these guys. Okay, and this is larger than this number, if you do the math. Okay, just like, okay, so the probability that this edge is good is up there, which means that in expectation I have got this number of good edges, which means that there is an order where this fraction of non-degenerate edges from, so now there's an order such that this fraction of non-degenerate edges are good, but the good edges survive in a normal depth of a minor. A normal depth of a minor has got this density, which means that the number of non-degenerate edges is bounded by this one. And this is this one times the inverse of this. Okay, and this is what we wanted to obtain. Okay, this is slightly more complicated than what I presented on the previous lecture, and I messed up something with this overlapping things and counting there. That was not true, and this is like the proof. In the previous lecture, we claimed something without the square here, and unfortunately, we don't know how to prove such things. Maybe it's actually the square is needed. The important information here is that really in congested minors, this one gets linear dependence in this quadratic. So that the one thing is, if this is polynomial in C, if this is like polynomial of degree k of A, then this one is the polynomial of degree k plus 2 of A. Okay? So not only like bounded expansion of G gives bounded expansion of depth A congested C minors, but also if the dependency, if these graphs were polynomial in A, in the radius, then also these graphs are polynomial in the radius. And this is something we'll be using, I think on the last lecture of this course, we will be using fact that something has the polynomial expansion to get approximation schemes. Okay? So this is something that I will be using on the last lecture of the course, or Michał will be using, probably me, I will be using, and that's, so maybe somebody will remember. Good. So I want to finish the things we screwed up on the previous lecture and go to coloring numbers. So wiping out everything and going back. No questions? Good. As Michał announced, or this fixed proof is already for the last few days on the lecture notes on the web page. I'm going back here to the start, and yeah. So now a small recollection. On the first lecture, I discussed with you some measures with regards to orderings. Yeah, we have got a graph G, and we were thinking of orderings. Yeah, sigma was an ordering of V of G, and we think of them as just putting vertices like one on a line. Okay. And in this order, there was, if we mark some vertex V, we had the notion of the strongly reachable sets and weakly reachable sets. Yeah, there was a strongly reachable set, and I put infinity here, and it was G sigma V, and there was weakly reachable set. Okay, and the intuition of the strongly reachable set, which will be in this color, this is actually green, okay, was that I'm allowed to make paths using the guys later in the order, so I can jump up here, and then I land up in somebody else. Yeah, so this was like all these guys U that are smaller than V, or smaller or equal than V in this order, okay, they are smaller or equal, so there is a path P from U, from V to U, so that all internal vertices, all internal are larger than V, are larger than V. Okay, so I can use the guys on the right and go here. Okay, and here I was allowed to use these guys here, but the endpoint needs to be the earliest. Yeah, so I was allowed now to go here. I was allowed to go here and maybe back here, and maybe here, but the endpoint needs to be the earliest. Yeah, so this was this. Two guys U smaller than sigma V, so there is a path P from V to U, so that the V is the minimum, U is the minimum. Sigma of V. Okay, so that the guy is the endpoint is the earliest. Okay, and obviously there was like this one was a subset of this one. Yeah, because if you can use only the later guys, you have of course the minimum up there. And one thing was important was that the V landed here. That always the guy, because there's a path of length 0 that starts in V, ends in the V, and V is the minimum guy and doesn't use any internal guys. Okay, so that was the definition. And what we were interested in, we're trying to, so there was a measure like strong calling number infinity of G and ordering was that the largest size, max over V size of this reach. Okay, I won't write everything, and this weak coloring number of G and omega was the maximum over V size of the reach. Oops. Okay, and now so we look, the quality of the ordering was the largest strongly or weakly reachable set. That's what it measured. And now we are trying to find the best ordering. Yeah, so like S-call of omega of G is the best ordering. And the same for weak coloring. And what was important, what we proved on the lecture, was that the weak coloring numbers correspond to tree depth. Yeah, that was I mean, lecture 1 was that the tree depth of G is exactly optimizing weak coloring numbers infinity. Yeah, that exactly the tree depth is really optimizing, and this best ordering is just making this tree depth decomposition going like top to bottom in the order, placing it in the order top to bottom. Okay, and what's also in the notes, and what we didn't do, but if you want to read the notes, was that optimizing strong coloring number is the same as true if. So true if plus of G plus 1 is the same as strong coloring number. Okay, and this is sometimes called perfect elimination orderings. This optimal coloring for this one. Okay, and now what we want to start and discuss, at least on this and the next lecture and maybe later lectures, is one of the most useful notions of structures in graphs of bounded expansion nowadays, graph classes. Namely, it makes sense to take another chalk and discuss paths that are of bounded length. Now I want to make, like, use the fact that I'm having a whiteboard or blackboard and doing some surgery here. So what I want to do, I want to bound the length of the path. For this notion, so now I define something, and it turned out to collapse onto three different trees depending whether it's weak or strong coloring number. So these are notions that are defined somewhere else and behave. And now, because in the true if is very well connected with the graph minors and not shallow minors. And we're studying here shallow minors, and it turns out that it makes perfect sense, and it's there's a lot to gain if we modify these definitions to add here of length at most r. Length of P is at most r, and add here length of P is at most r, and then flip this infinity that corresponded to no bound on the left path and put r here. And now all the infinities becomes r's. Okay, and yeah, so now what I'm doing now is that I'm restricting this definition to allowing only guys to reach up within some distance. So this path, this green path and this blue path, witnessing that somebody is in the strong reachable set and weak reachable set, needs to be of bounded length. Okay, why this is okay? So why this notion makes any sense? I mean, this is a proper definition, but why it's maybe useful. The first useful is that as the length of course, as my restriction of the length grows, the sets grow. Okay, because I mean I allow more and more paths. Okay, so strong reachable set of 1 is contained in 2, is contained in 3, is contained in 4, etc. Okay, so these sets grow, and in the limit they somehow like converge to something related to true if, and in this guys in the limit converge to something related to true if. Okay, but what I want to make an observation was that, hey, what happens for r equal 1? For r equal 1, I mean both the strong reachable set and the weak reachable set is the vertex v and all area neighbors. Okay, because the only paths allowed of length 1, which means that there needs to be only direct edges going there to somebody area. Okay, so then we reach r which 1 g sigma v is the same as strong reachable set 1 of g sigma p, which are the area neighbors, which are these neighbors, which is v plus this u in n of v plus u is smaller than v. Okay, that means that what optimizing this, so we are looking at the number of area neighbors. This is something we optimized on the first lecture. Yeah, this was the generous. Yeah, which means that v call 1 of g is the same as s call 1 of g, which is 1 plus the generous. Yeah, because of I mean the generosity is I mean this 1 comes from the fact that we count v here, and the generosity we just count the area neighbors. That's this 1 extra here. Okay, so this weak reachable and strong reachable sets, I mean they form some sort of continuous or semi-continuous scale between the generosity and true if or true depth. Okay, yeah, I mean up there. I mean, at least optimizing them. And yeah, so now it turns out, and that will be the main focus of this lecture and the next lecture, is that they're very, very closely connected to our previous definitions that we had up there. Okay? Now what I want to prove here, that, well, these are two different notions. And now, but what I want to prove is that you cannot have an ordering that have got small, strong coloring number, but huge weak coloring number. I want to say that if these guys are small, these guys cannot be much larger. That's my proof, okay? For a fixed ordering, I cannot, I mean, these numbers. For a fixed ordering, I can't have tiny, strong coloring number and huge weak coloring number, okay? But for that, we need an extra tool. So we need a third way of measuring some sets up there, which will be useful, which is, I'm not sure if not historically one of the first, but it will be useful like intermediate measure, and it will be also useful for some algorithmic application or some algorithmic application that we'll study on the tutorials. So let's define admissibility, okay? So what I want with admissibility, so let's, again, I have got the vertex G, I have got some ordering of this of G, and I have got some fixed vertex, and I want to look at the admissibility with some radius R, again, this vertex G and sigma and V, and I put here normal brackets, not the square brackets, because this is a number, not a set. This was a set, this was like reachable guys in some fancy way. This is a number, this is a maximum, this is 1. This 1 plus maximum set of family of paths such that P is a family of vertex disjoint paths except for V. They can share V, that start in V, and in U smaller than V, I mean, and it's a vertex smaller than V, and additionally have length at most pair. Okay, that was super complicated. Let's draw a picture. There's the ordering. There's somewhere vertex V here, and now let's use pink. There was something before. Okay, and what I'm allowed to make paths and somewhere here, and I cannot use a vertex twice. I start from V, so V is used multiple times, but a vertex cannot be used more than once. So I can take a direct edge, somebody area. I can jump here, maybe jump here, and then jump here. Okay, and yeah, maybe there's some extra edges, but I mean, this path really need to be vertex disjoint, so this is like really smaller. Yep. So what I want to say here is that, well, okay, so that's the definition. Okay, this one here is like the analog of the fact that in weak and strong reachable set we include the vertex V. So you can think as like a vertex V is an extra guy counted here just because he's V. Or there's a 0th path on top of all this family up there. So V is like this plus 1, this one's for V. This plus 1 is for V. Okay? Now what I want to say is that I can assume, and I will write in pink because that's not part of the definition, that every path, it has all internal vertices to the right. Yeah? If I have got this path, look at this path, it goes here, then here, then here, I could have shortened it and just count these vertices. Okay? Because this path where vertex is joined, this vertex is not used by any other path. Okay? So I could as well, instead of going here and here, I could just stop here and count this guy in the admissibility, not this guy in admissibility. Okay? So I can assume that for every P and P, or internal, it is I larger than V. I can just stop this path whenever on the first vertex smaller than V. Okay? And that would be fine. Okay? So I can think of only such family here. Okay? Good. So now what it proves here is that the admissibility, what I want to say here is that what would prove like of the three observation now is that the admissibility of a vertex G sigma V is of course smaller than the strong reachable set R G V sigma v? Well, because I mean all these paths, these family of paths, witness that all these guys that we count here in the admissibility are in the strongly reachable set. Yeah, I mean this guy. Yeah, if we shorten the paths, then what we have here, we used green, is that this guy and this guy and this guy are in strongly reachable set. Like the first earlier guy and of course v. That the first guy on every path that's the left of v is in the strongly reachable set of distance r, which means that the admissibility is smaller. Okay, and again we can have the same blah definitions like admissibility r of g sigma is the maximum over v admissibility r of g sigma v, and admissibility of r of g is the minimization over sigma admissibility r of g sigma. Okay, so we are again trying to have as the best possible worst. I mean, we want to minimize the largest admissibility. The largest. You can think of it as a flow, but it's not really a flow because we bound the length of the path, so we cannot use that easily flow techniques to find admissibility at some point. That's not that easy. Okay. And what we want to prove now, and this is up there, we want to prove here that admissibility, of course, admissibility is smaller than strong coloring numbers, which is smaller than weak coloring numbers, and now we want to make bounds in double directions. So we want to first say, okay, so we have, of course, the admissibility R of G sigma is smaller than a strong coloring number, R of G sigma, which is smaller than weak coloring number of G sigma. And now we want to make two lemmas saying that this one cannot, if this one is tiny, this one is small, and if this one is small, this one is not too large. Okay, there will be some blow up there, but if this one is small, this one cannot be very large, and this one is reasonably small, this one is also not super huge. Okay, and that's the plan for the next 20 minutes to show that actually, like, you cannot have one of them tiny and the next one being super huge. I'm going here. And okay. And these two lemmas that we've just shown are not super difficult. I mean, I think the only difficult proof won't fit today, and we'll do it on the next lecture. So let's do lemma 1. Let's now compare admissibility and strong coloring numbers. I want to say that strong coloring number of R of G sigma cannot be larger than, I think, 1 plus admissibility of admissibility R of G sigma is 1 power R. So there's power R here, yeah? So if this is tiny, then there's tiny to the power R we think constant, so this is also small. Okay? So proof. Let's think of the strong coloring numbers in the following terms. One important thing, I'm not using here, like for every vertex V, the strong coloring set is not larger than the admissibility of this vertex. For fixed vertex V here, I will be using admissibility of many vertices in the proof. I will see it in a moment. Right? So we fix G sigma, we put some vertex V of G, and we want to like bound the size of the strong mutual set of R G sigma. Okay? And I will look at the admissibility bound. I will use the admissibility bound for many vertices up there. Okay? So what I want to do, I want to somehow canonize these paths. Like every vertex in the strong reachable set, yeah, we have got this ordering. There's somewhere vertex V here, and there are some paths that were green on the first picture. There are some paths up here that go up there. Some guys from the strong reachable set. In some sense, I want to canonize these paths. Yeah. Look what happened here. We went hop, hop, and went back. and for the other guy went here, here, and went back. Okay? I want like to make this. I want to make this one, what happens on the right, to be a tree. Like I make some tree here, and then jump here. Okay? And because this path needs to be of length at most r, so I need to control the distance. The natural thing is to take a BFS tree here and make all these guys from the strongly each other sets leaves of this thing. Okay, let us write it here. So let's take T. This is a BFS tree from V in what I win the graph induced by this U larger than V. Okay, so I take all these guys that are here and run a big BFS from V. Okay, breadth first search from V, so like the shortest paths. Okay, and what I want to say is that up there, and what I want to say here is that for every W in the strongly each other set, well, except for V, let's count V. V is this one. This is V in the statement. So let's don't count V. Okay? In this strongly each other set, I want to fix a path that's just going down this tree T and then jumping on the last edge. Okay? Yeah, because this is the shortest path tree. So a guy W here, okay, it has got his path. I mean, it was like this path going here, and going back here. Okay? And what I want to say here is that, well, there was this last edge that went earlier, but I want to make this first part of the path the shortest path from the tree T. Okay? I want to replace, so every vertex W had his path witnessing that he is in this strongly each other set, and I want to canonize this path by taking the prefix from the tree T. What I want to say here is that there exists a path P, W, which is from V to W, okay, of length at most P, at most R, such that it's like, such that P W minus W is a path in the tree T. Okay, so there's this tree T here, somewhere here, and I can reach this vertex by going by a shortest path in the tree T. So this may actually be a path going like this. Okay, so I can take yellow here and then take this last edge here to witness that W is the strongly each other set. Okay, so I can make another tree. So let's make tree T0, pink one. T0 is the union over all W's in this strongly each other set. In the strongly each other set R, G, sigma V. Okay, this path is W. Yeah. So this path, this tree, is like a subtree of the tree T, and a number of like leaves for strongly each other set. Yeah. So I want to say that leaves of T0 are strongly each other. R G sigma V minus this like V doesn't count here. Okay. So I'm building this tree. I mean, what I'm saying is that in this T0, I found a subtree, which is like the shortest path for the guys from the strongly each other set, plus this last hops towards the guys from the strongly each other set. Okay? So this is T0. I rooted T0 is rooted at V. At V, and it has got depth at most is at most R. Okay, this is a tree which has got depth at most R because these paths are length at most R. And the important observation here, what I want to say, is that the degree, the number of children, is bounded by admissibility minus 1. Crucial observation is that for every U in T0, the number of children of U in T0 is smaller than this number. That's fine. Why this has happened? Well, let's draw the picture here. Well, if there's a vertex u, so suddenly in this tree there are many children. So some of the children are hops later, and some of the children are actually edges going earlier in the order. Okay, up there. And now all these paths that go later, and they lead to some leaf because that was a union path. So there's actually some hops going up here, and they eventually end up with some leaf. Maybe many leaves, but at least one up there. What I'm saying here is that if there's a vertex in this tree T0 that has every child gives a different disjoint path towards somebody earlier, towards somebody here. Okay, because below every child there's a leaf, and the leaf is a guy from the strong reach set here, which means that for every guy here there's some path that ends in a guy earlier, actually here. So starts from here and ends here, and there's a vertex disjoint because they go to different subtrees of this tree. Okay? Which means that this guy cannot have more than the admissibility -1 because he also counts in his admissibility. Okay? So he cannot have more than admissibility. And now we're done, yeah? Because the strongly reachable sets are leaves, depth is R, number of children is this one, which means that the number of leaves of this tree is bounded by this. Yeah? If I have got a tree, such that every vertex has got at most this number of children, and the depth is this one, then this is the bound on the number of children. A full this array tree of this depth has got this many children. And this +1 is vertex V. Okay? So what happened in this proof? Well, we looked at the way how this weaknesses for strongly reachable set for being a strongly reachable set looks like. There are like some paths. We said, hey, as well on this area to the right of V, you can use some canonical shortest path tree for the shortest paths towards guys that will finally go to your guy from strongly reachable set. And the admissibility bounds the degree of this tree. And whenever there's a in this tree, the admissibility governs the degree, which means that this tree cannot be too large. So that's the proof of this one. And okay, so now let's go to the other proof, which will be of the same flavor. Namely, now we want to go with the strong corollary numbers and weak corollary numbers. So let's wipe it out. Now I want to do lemma 2. Lemma 2 says that I cannot have tiny strong corollary number and large weak corollary number in the following form. Corollary number R of 3 sigma is smaller than, again, I need to probably say 1 plus strong corollary number R, which is sigma minus 1, or R, but there will be like also R in front. Okay, so this is like slightly worse function than the previous one, but very similar. So the proof may be sort of similar, but not really. Okay, so let me try to do it this way. What I want, the intuition is as follows. Now let's make the proof, and I will make the intuition out of which many of you can figure out the proof. This is my ordering. Okay, and there is like vertex V. Now what I want to say, let's have a guy from W. Sorry. Let's take a guy W in the weakly reachable set. R sigma B. Okay, and what I want to have here, I want to have, and let's take the weakness path. So this is the weakness path. May go here, may go earlier, may go a bit later, may go here, may go earlier, may go here, may go earlier, and may go here. Okay? And what I want to say here is that I want to define here milestones. A milestone on the path is like the earliest guy we have seen so far. Okay? So I start from V and go, this is like the first milestone, okay? And I go here, this is later, this is later. Ah, I have never been so early before. This is milestone 1. Then I go here and here, this is later, I have never been so early before. This is second milestone. Okay, then I went here. Oh, I have never been so early before, and I have never been so early before. Okay, so I pick. So I have this picture. Let's make formal definition, and let's pick a vertex path PVW. Yeah, this is the path witnessing when W is in this W region. R G sigma V. And I want to say the milestone is the guy that's earliest on the prefix from V to this place. And I want to say that VI on PV is a milestone if VI is the minimum of PVW from V to VI. Yeah, on this prefix from V to VI. Okay? So what I want to say here is that okay, and like what I want to say here is that I go on this path from V to W, and whenever I'm at the vertex that's the earliest so far, I say this is a milestone. Okay, and let's have V0, V0, V1 up to VL being W, the milestones. Of course, W is the milestone because W is the minimum of the path, so it's like the last milestone we encounter on the path. That are milestones. And the crucial observation of the proof is that the next milestone is in the strongly reachable set than the previous milestone. Okay? Because between the milestones, we use the guys later and then jump to something earlier. This was the earliest guys we have seen so far. Then we use somebody later, some things later, and then we jump to something earlier. The crucial observation is that Vi plus 1 lives in the strongly reachable set of R of G sigma Vi. Okay? This is the crucial observation. So now, how many such sequences can we generate? Yeah, we start from V0, and then we go to somebody from the strongly reachable set, somebody from the strongly reachable set, somebody from the strongly reachable set, and some moment we stop. Okay? So there's like one so how many such sequences? How many sequences of milestones? Well, there's one sequence of length 1. Okay, this is of one vertex, just V. Okay. Then, well, this we can choose this guy to be in strongly reachable set of the previous guy. So this is first called R sigma minus 1. Okay. This is of length 1, of length 2, these sequences. Then we can choose another guy. So this would be like squared, because we choose this guy from the strongly reachable set here and the V2 from the strongly reachable set here up there. And similarly. And this path, this sequence of milestones can be of length at most R, because that's the length of the path. Yeah? I mean, that's so this is like. R, and now if you do, so this is like sequence, this is the largest term, and this is a brute force estimation that all these guys are not larger than this term. Okay, and this is this sequence, and this sequence determines W. I mean, you start, like, in a sense, you take V0, you look what's the next milestone, what's the next milestone, what's the next milestone, stop. And sequences of length 1 are this number of length 2, this number of length 3, etc., this number of length R plus 1 actually. Okay, so this is the bound on the number of sides of the weak reachable set, because the sequence of milestones determines the endpoint. And now this one is smaller than this one, because this is a brute force estimation that all these terms in the middle, this is the largest guy in the sum. The last one is the largest guy in the sum. Okay, so that wasn't very, yeah, that was like playing with the things. So now, about these three things. So we had admissibility, strong correlating numbers, and weak correlating numbers. My experience from work here is that what we'll see in the lecture or the tutorials is that the admissibility was useful in the proofs, and we'll use it once also in some other proofs, but it will somehow like disappear and won't be that useful in the theory. The good thing about admissibility is that the best ordering for admissibility is polynomial time computable. I mean, we won't see that exactly on the tutorial, but we'll see a decent approximation, which will be very simple on the tutorial. But we'll try to understand why it's really like there's some like greedy approach to computing admissibility thing which works, whereas this greedy approach doesn't really work for weak coloring numbers from correct numbers, and they're harder to compute. We had made some experiments how to compute weak coloring numbers, because later we'll see that in theory the weak coloring numbers will be the most useful. I mean, they will be the most useful tool, like orderings of small weak coloring numbers will be the most useful tool. And we actually made some experiments with Wojtek Nadala, who was at that moment master student, on computing them, and some greedy approaches similar to what we'll be doing for admissibility works the best, but there are no really bounds on how well they behave. So computing weak coloring numbers is quite an open thing how to really do it properly. I mean, you can do some approximations and compute decent ones, but how to compute them optimally and how to lower bound and how to certify that the weak coloring number can't be too small nicely, there's quite large gaps there, and there's quite a number of open problems. So this is about things. We have proven here that we have got these three numbers. Admissibility is smaller than strong coloring numbers, smaller than weak coloring numbers, but they are bounded like one cannot be much larger than the previous one. So there's some function like previous one to the power r that bounds the next one in this line. Okay. So now, as last proof today, we want now to connect these weak coloring numbers to the density of shallow minors. Okay, that's what we had on the previous lecture. We were looking at the density of shallow minors, and what we want to do now, we want to now connect these two theories. Yeah, I have built for the last 40 minutes or something like that. I have built a theory of like 3 different ways of measuring orderings given some radius. And they're nice to play with each other, and they were nice colorful pictures, but what's the connection to the density of shallow minors we have discussed previously? So there are 2 lemmas. I will prove one and leave the other one for Michał for like 2 weeks, because next week there's no lecture. And yeah, so let's try to do it, and I want to wipe it out and try to prove it. The lemma that I want to prove, and this will be like the simpler lemma, the difficult proof will be left for the next lecture, is so let's call it lemma 3. The lemma 3 is that if you have got small weak coloring number, you cannot have 2 dense shallow minors. So like what I want to say is that nabla R of G is smaller than the weak coloring with 4R plus 1. So if the graph G doesn't have too large weak coloring number of radius 4R plus 1, it cannot have got 2 dense R shallow minors. Okay? So this will be like the connection, like a good ordering with small weak coloring numbers is a certificate that you cannot have 2 dense shallow minors. Okay? Let's prove it. Well, let's say, I mean, we have got this one, we need to use it, so let's take the order. So let's take the sigma is the order. Yeah, so we take the best order up there. Okay, this is like the best order. And now we want to show that what we really want to show, we want to take a shallow minor and find a guy of small degree. Okay, we want to prove that the shallow minor is degenerate. Our goal, so let's take H is R shallow minor of G, and let's take the branch sets model, and what I want to do, I want to find what I want to find a vertex of degree at most this thing. So I want to find H0 in V of H of degree at most this. Okay, what I want to do is that I want to find the minor and say, hey, every minor, a shallow minor, has a vertex of this degree, of at most this degree. And that's enough, because then I peel out this vertex. I have got again a shallow minor. I have another such vertex, peel it off, peel it off, peel it off, and I have got the generosity bound on this shallow minor. This is actually like bound on intensity. Okay, so I want to prove that every vertex, every shallow minor, has got a vertex of this degree. So I'm really proving that the R shallow minors are this degenerate, this number degenerate. Okay, that's my goal. The intuition is that it should be the last guy in the ordering. Yeah, the weak coloring number is something resembling the degeneracy ordering. Okay, and like if you have a degeneracy ordering, the guy that has got in a subgraph, the guy that has got the small degree is the last guy in the ordering. Okay, and we want here to use the same fact that in some sense the weak coloring number is the degeneracy ordering for radius r distances. Okay, let's make it formal. So what I want to do, for every branch set, I want to look at the earliest guy in the ordering. So f of h is the sigma minimal element bh, and h0 is the guy with largest b of h. Is the one with f of h being sigma maxima. Let's make a picture. Let's make an ordering. Let's draw 3 branch sets because that's the amount of colors I see in the world. So there's some branch set that uses these vertices. This one branch set. Another branch set uses these vertices. Okay, and another branch that uses this vertices and maybe this vertex. Okay, so now this one is the f of h1. Okay, this one is the f of h2, and this one is the f of h3, and h3 is h0. Okay, in every branch set we look at the earliest guy in the order, and we choose as our favorite guy, the guy that has got the latest, the earliest guy is the latest. This is the analog of this data in the degeneracy ordering. If we want to prove that every subgraph has got a guy of small degree, the last guy in the ordering will have got small degree because all the other guys are his left neighbors. Okay? And I want to now say that, well, this guy, what I want to now prove is that for every h0 in E of h, so for every h in this minor, actually f of h is in the weak reachable set. G sigma f of h0. What I want to say here now is that, well, if there is an edge in the minor from this h0 to h1, then this guy is in the weak reachable set of this guy. And there's for r plus 1 here. Okay? And that will be the bound, yeah? Because, I mean, this guy, for every edge, gives a guy in the weak reachable set, which means that the number of these edges can be larger than the size of the set, which is bounded by the weak coloring number. Okay? And this is quite easy, because, well, what does it mean to partial minor? That means that there's a path P h0, which means that, okay, what does it mean? That means that BH touch BH0. Okay, that's because there's an edge. They need to touch each other, which means that I can draw a path P that starts, let me draw it here, a path P that starts in f of h0, goes somewhere, and this will be like, this is BH, this is BH0, and I can draw a path that goes through this blob, goes through the touching place, and goes somewhere here to f of h. Okay? I can draw this path. And how long is this path? Well, this part is at most for r, 2r, because this one has got radius r. Yeah, so I could be in external place of something with radius r, so there could be 2r between them. This path is at most 2r for the same reason, and I draw here an intersection, but this could be an edge. Yeah, they can touch by an edge, so there can be like one here. There can be one here if this is an edge. So that gives this order. So the length of the P is at most 4r plus 1. Okay, so these guys are connected by through this blob and through this blob. So there's the path, and this path is contained in the blob BH and BH0. Okay, because I use this blob and I use this blob only. Okay, and now what comes the definition of F. Yep, I want now to show that P proves this. This path P is a witness that f of h is in the weak reachable set. That if there's an edge, this guy is in the weak reachable set of this one. I want to say that this guy is the earliest guy of this path. Okay? Why? This one is the earliest guy of the blue set. This one is the earliest guy of the yellow set. And by the choice of the h0, this guy is later. Okay? Which means that this guy is the earliest guy out of the blue and yellow set, and the path lives in blue and yellow set.
Can these sets BH actually intersect?
No, they can't. I was doing congested minors before, and that's why they can't. Excellent question, thanks. That's my confusion from lecturing. This is this one here. So this is this one here. Thanks. Okay, so I have this path, so because there's an edge in the minor, there's a path I can go through this blob distance r, jump over an edge and go through this blob distance at most 2r to this f of h, this earliest guy. And this path is of length at most 4r plus 1, and this guy is the earliest guy on the path. Because it's the earliest out of the blue guys by definition, this guy is the earliest out of the yellow guys by definition, and the choice of h0 says that this guy is later than this guy. Okay? Good. So we have proven this one. That means that this guy is degenerate by coloring numbers, and we have got this very nice inequality, which is quite clean, and not that clean as the second one. So for the second one, I want to just draw it, write it down, and first find it, and then write it, and then discuss the consequences of it. Okay. I'm moving to the other board and using lemma 4. So what I want to say, I want to write lemma 4 now, which will be proven on the next lecture, proven on the next lecture. And now I just want to discuss corollaries of it, that the admissibility of G is smaller than 1 plus 6r times the seal of the topological minor to r minus 1 of G times to power 3. What does it mean? What does it mean? Well, if I don't have dense topological minors, I cannot have too large admissibility. Okay? And this is like really the connection we made. Eh? The previous one says, hey, you cannot have too dense minors. You cannot have too dense minors if you have got small weak coloring number. And this one says that you cannot have large admissibility if you don't have too dense topological minors. Okay? So what we obtained, now let's summarize, because that's a very important step in this theory. We have obtained the following. We have got this bounds in terms of these ones. We have got the bound, the other ones, that delta r of G is smaller than weak coloring number. And we have got this lemma saying that these guys are roughly the same, right? That admissibility R of G is smaller than strong coloring numbers, R of G is smaller than the weak coloring numbers. And if you pipeline everything, this two lemma that we had, there is something like 1 plus R admissibility R of G minus 1 to R squared. If you pipeline the two previous lemma there. Okay, so there is something like that. So what does it say? It says that if any of these numbers is small, this number is small, and also all these things are small because on the lecture that Michał lectured 2 weeks ago, he related these notions to these notions. The nablas and nablas tildas, the topological minor density and the minor density. Okay? So what it really proves here is that if we have, let me write it, let me just take the, so we have got the following, if G is the class of graphs, then the following is equivalent. The following is equivalent, like G has bounded expansion. There's a function, and I want to say that there exists a function f such that for every r, for every G in this graph class, the weak coloring number, the algorithm, the admissibility of R of G is the smallest f of R. So this is like f1. The strong coloring numbers of G is the most f2 of R, and the weak coloring numbers R of G is the most f3. So this is like f1, and there's exists f2, there exists f3. So there are like 4 equivalent conditions. We have got a graph of bounded expansion, or admissibilities are bounded as a function of R, or strong coloring numbers are bounded as a function of R, or weak coloring numbers are bounded as a function of R. I mean, if you gain any one of these, you get all of them by all these inequalities. Okay, because they sometimes blow up the radius, sometimes blow up there, but on top of like bounded expansion that says that for every R there's some density bound for minors, or for every R there's some density bound for topological minors. Well, it's equivalent to saying for every R there's some bound on admissibility, or for every R there's some bound of some strong coloring numbers, or for every R there's some bound on weak coloring numbers. Okay, so and this is like the first moment in this theory when we have got this notion of bounded expansion turns out to have like 2 different angles. There's the angle of density of minors and the angle of the ordering, the quality of the orderings. Okay, and what's very interesting in this theory and was very powerful was that will it prove like 2 or 3 more such equivalences. There will be some neighborhood complexity, there will be some other notions up there, like low 3D colorings, and they will be also of the same form that some object is of bounded size or of bounded quality up there. And in many proofs, we'll be saying, well, we have got a class of bounded expansion. Which tool will be most useful? Actually, for this proof, coloring numbers are the most useful. Or for this proof, actually, density of minors is the most useful. So in the previous lecture, we have made quite an effort to prove that if I blow up every vertex into, okay, so we, at the beginning of this lecture actually, we made quite an effort to proving that the congested minors are also sparse, okay? We did it mostly to get this decent bound up there that we'll be using later. But if we don't care about the actual bound, but just saying, hey, if the guy is sparse, then the congested minor is sparse, maybe slightly more sparse, but still sparse, on the tutorial we'll show a 1-line proof of that fact. Okay, but the point was that to ignore the density and look at coloring numbers. Okay, good. Good, so this is this one. And now there's another observation on top of it, saying that, well, these bounds, I purposely put them over here because these bounds are all polynomial. I mean, there's some R in the exponent if you treat R as a constant, but they're all polynomial. Okay? And remember that for nowhere dense, we had these graphs bounded by like f of R epsilon times v of g to epsilon. Yeah, for every epsilon, for every r. Okay, we had got this bound. Okay? Yeah, there was the bound that density of shallow minors is bounded by it's sub-polynomial. Okay? And the point is here that we have got these bounds. These bounds are polynomial. Okay? And there's this constant r up here there. and there's this bound up here, and the relations here are also polynomial. So what I want to say is that phi, like theorem, what you can deduce from here is that actually the weak coloring numbers in the nowhere dense graph classes, because this is bound expansion, nowhere dense classes are also good. Okay? So like what I want to say, if the class G is of nowhere dense, then there exists a function f, say hat, such that the weak coloring number R of G is smaller than f of R epsilon, v of G to epsilon for every G in this graph class, for every R and for every epsilon larger than 0. Okay? So that what you can deduce by just pipelining and playing with putting epsilon to be the other epsilon over R and doing a number of this type of manipulations, but by taking this one and pipelining the correct dependencies here, observing that they are always all polynomial if you treat R as a constant, you get that actually the weak coloring numbers in bound nowhereness graph classes are okay, not constants, but not constants depending on R, but the dependency on the graph size is like n to epsilon. Of course. Yes. Okay, good. So this is the thing I want to say here. I want to say the last punchline about writing up, about not writing, but computing the things. If I have the correct notes, I don't have. But what I want to say is that actually the point of one of the points of using admissibility, I want just to have the correct running times, and I made some I made no mess with my notes. So yes, here it is. Good. What I want to say here is that last sentence or last thing on this lecture is that computing things actually, like computing admissibility, we'll see parts of this on the tutorial, but what I want to say is that if G is class of bounded expansion, and R is the constant, then one can compute the like admissibility are optimal ordering in linear time. Yeah. So what does it mean? I fix a graph of class bounded expansion. Okay. So these guys have linear number of edges. So this is linear in the graph size. Number of vertices is linear in the graph size, and I can compute in linear time admissibility optimal ordering. So this is a decent ordering for strong coloring numbers, for weak coloring numbers, but our inequalities on our board. And but the problem here is that there is like huge constant depending on R here. Huge constant depending on the graph class and R in front of it. Okay? But it's linear time for fixed cross of bound expansion for constant. What we'll be doing on the lecture is that there is an R approximation with tutorials, an R approximation in time O of n cube m, but no cheating on Asian graph class. This is arbitrary graph and R only in the input. Like it takes graph and R on the input, works in this time, and produces an R approximation of the admissibility ordering. Like ordering that has got admissibility at most R times the best one possible. Okay, and in some sense this may be sometimes useful. Okay, the bound here, there's like polynomial here, quite substantial. You can try to punch it down. We're doing quite brute force in this algorithm. But the point is that if you don't like huge constants depending on the graph class, in any graph class you can do R approximation, which is some constant approximation of the admissibility ordering in polynomial time. So that's things, and I think I want to stop at here. Thanks. There's the